First of all, welcome to this year's Chern-Weil Symposium. We're very happy to have as a first speaker, Martin Heyer from PFL and Imperial College. Martin works at the intersection of probability, stochastic differential equations in mathematical physics. A number of very important breakthroughs in these areas. He has received many honors and prizes. Let me just mention the Fields Medal in 2014. His work on regularity structures, the Breakthrough Prize in 2021. But this is just a small sample. So anyway, without further ado, Michael.
Thanks a lot for the introduction. Thanks a lot for the invitation. Always a pleasure to be here. Unfortunately, I won't stay very long this time. So the aim of the lectures, I'm not going to assume that you know what the title of this talk is about. And so basically the main goal is going to try to sort of explain the problem to you and show what result we got. Okay, and so the point will be to essentially get you to sort of understand the statement of the main results. That's going to be the goal, and to sort of understand the words that show up in the title. So the context here is the context. Oh yeah, maybe I forgot to mention. So this is all joint work. So it's based on two papers that are both on the archive. One is published already in the Publication de HRS, and the other one is just been accepted as Invenciones. And both of them are joined with Ajay Chandra, who's also at Imperial, Ilya Chevyrev, who is in Edinburgh, and Hao Shen, who's not very far from here in Wisconsin. And so the context here is that of Euclidean quantum field theory. And I'm not going to explain, so there is a relation between Euclidean quantum field theory and real quantum field theory, if you want, which was sort of explored by Osterwalder and Schrader back in the 60s. So I'm not going to spend any time on that. And so I just asked you to take it on trust that what you should do in Euclidean quantum field theory is the following. So you're given an action functional on some space of fields, and the easiest example, right? So the sort of example of action functional that you should have in mind is, for example, s of phi equal to, say, a half of the integral of gradient phi squared. Right? So that would be the Dirichlet energy. And so your action functional takes as an input a field, which is a function of some domain, the domain being your space-time, and it spits out a real number. Okay. And the action functionals that are relevant are always local, right? In the sense that they are of the form an integral over your domain of something which only depends on the field at that point, right? Basically just a local function of the values and the derivatives of your field. And that's somehow this structure encodes the fact that you want locality. Right? So you don't want sort of instantaneous transmission of information. And then given such an action functional, what you want to do is you want to build a probability measure on the space of fields, which is, if you want, like the Gibbs measure that's associated with the action function, right? So like formally, it should be e to the minus constant times your action functional times the Begg measure on the space of fields. And of course, you've all learned in your undergraduate studies somewhere that you cannot define the Begg measure on any infinite dimensional space. is you cannot find any, sigma additive measure that's also translation invariant on an infinite dimensional space, because, well, if, say, the unit cube had measure 1, then, the cube of twice the size would have to have infinite measure. It's made up of infinite unit cubes, right? And so you can't really define non-trivial sort of Lebesgue measure on infinite dimensional spaces. But then the hope is that if you have an expression like this, well, what you can do is you can always discretize things, right? So you can replace your infinite dimensional space by a finite dimensional space, basically meaning you discretize your field, you replace the underlying domain by the grid or something like this, or maybe some other way of discretizing things, maybe Fourier space or whatever. And then, you figure out some analogous discretization of your action functional. That gives you now a sequence of measures. And then if you're lucky, that sequence has a limit. And if you're even luckier, it has a limit that doesn't depend on how you discretize things in the first place, at least within some reason. Turns out in this business, you can always come up with crazy discretizations that give you pretty much anything you want, but you also reasonable discretizations are somewhat spatially homogeneous in a way. And then, if you get a limit that doesn't really depend on how you discretize things, then that would be your candidate measure. Okay? And then, of course, the same kind of structure that shows up in statistical mechanics, right? So for completely different reasons, where this action function would be the energy of your system, and then the Boltzmann Gibbs distribution has exactly the same form. So that this problem of constructing measures of that type is a very common problem in probability theory. But so the example that we're going to discuss today is that where the action functional is what's called the Yang-Mills action, and that, to the best of my knowledge, only has the quantum field theory motivation, not statistical mechanics motivation. So, okay, so now what is the Yang-Mills action functional? So in this particular case, the situation that you have is that you have so in general, you have a principal bundle, but forget about that. So you just, you have some phase manifold, which in our case is just going to be the torus. And then at every point, you attach a copy of some Lie group G. Okay, so you fix a compact Lie group G, and you can think of something like, SU2 or something. The interesting case is the one where the Lie group is not a Lie. Of course, the most basic case is the one where your Lie group is U1, which is just a circle, which is a Lie, but that's the one where you can draw pictures on the board. So you imagine you have a base space here. At every point, you attach a copy of G. So that's your copy of G. But then, what a principal bundle really means is that you think at every point you attach a copy of G, but you forget about which element of G is the neutral element, right? So like a group comes with one distinguished element, which is the identity. But then, of course, you can also view the group as a geometric object on which the group itself acts by multiplication. Right? And then, as that geometric object, there, the identity doesn't play a special role anymore. Right? So, in the group itself, like in its action, of course, it plays a special role. It's like the identity action. But the space on which it acts, which is again just a copy of the group itself, there the identity plays no special role. Right? Like in the circle, take the circle as a circle. Well, there's no point on the circle that looks different from any other point. But if you view the circle as a group, then, well, one of the points you decide that this is the identity, and then the others give you a certain angle from the identity, and the way it acts on the circle is by rotation at that angle. Right? So you really think of your space, the space here, as being a copy of G attached at every point, but you sort of forget, you think of the G as a geometric object, you forget about which point is the identity element, right? Because the way you write things in coordinate, then you have to write things down in coordinate, then again, you have to make a choice of which one's the identity element. Is the identity element, but that choice is sort of arbitrary, right? So if you want the analog in this business of doing a change of coordinates is you leave the base space untouched, of course you can also make changes of coordinates in the base space, but then that is leaving it untouched. And then you can, at every point, you can sort of rotate, right? You can do a change of coordinates of which point here you consider to be the identity element. So you can do so the natural changes of coordinates here are maps that go from your torus into the group itself, right? And now what the fields that we're considering are now connections on such a space. And what does this really mean? So a connection is still with the color choice. No. So a connection. So no, don't worry. Just over here. It's okay. That could just do the same thing on the screen. If you want it. Oh, don't. Okay, cool. Thanks. Okay. Thanks a lot. So what's a connection? A connection is a way of lifting curves. So take a curve down on the torus, okay? And now you want to lift that curve for a curve on the full space, right? The full space being a copy of the G attached at every point. And so now what you have to do is you have to specify a way of doing it, right? Now, if you had, if it were the case that at every point there's a distinguished element, like the identity, well, then of course there's a natural way of lifting it. You just, at every point, you say, well, I simply lift to the identity of the copy of G that's over that point. But we just said that we want to view G as being, having forgotten about which element is the identity, right? And then I don't have any canonical way of lifting it anymore. And now a connection gives you a way of locally lifting, right? So it's not a global choice, if you want, of the identity above every point, but it's rather a local choice of how to lift the curve, where it says, well, suppose that this blue curve here, I sort of lifted it, say, I don't know, so I lifted it to a red curve somehow on the full space. And so now I'm somewhere here. And so that's the lift of this point here on the blue curve, right? So now what do I have to do? I choose, right? So I have a direction in which I'm moving downstairs along the blue curve. And so now I have to specify, you know, how this makes me move upstairs on the red curve. So now if I'm given a coordinate system, which means that, you know, I make some arbitrary choice of which one is the identity of how to parameterize these copies of G, then what this means is that I'm really given a one form which takes as input a tangent vector of the torus downstairs, and it spits out the direction in which you move upstairs in the copy of G that lives above that, right? And the tangent space of a Lie group canonically identified with the corresponding Lie algebra, right? And so a connection in this context is really identified with a one form on the torus with values in the Lie algebra. But it's not canonically, right? So like connections and one forms are not exactly the same because that identification relied on a choice of coordinates, right? Like if I change my coordinates, so I change which, you know, I do a rotation of these copies of G, but at different rotations at different points, then that's going to change that one form, right? So it's going to give me a different one form. But anyway, there's this natural identification between connections and one forms. And then the action is the natural curvature, the integral of the curvature, the square of the curvature tensor that goes with it. And curvature, so what's curvature in general? Whenever you have principal bundle, the curvature is essentially, you have a notion of lift, like I just described. Or if you want parallel transport, which is also lift. And then the curvature is, it tells you like to what extent things don't close up if you go around a little loop. Okay, like here, I can take, instead of having a blue curve like this, I could take a blue curve, which is a small, tiny loop of the torus, and then I can lift this. But because the way of lifting was local rather than global, right? So it tells me that that little blue curve, it sort of goes lifted into a little red curve, but the red curve doesn't necessarily close up. And then you look at the discrepancy, like by how much does it fail to close up? And now that's, what does this give you? That gives you basically a two-form, right? So you have to specify a little loop. A loop is essentially described by two vectors, which gives you the plane in which your little loop lies. The amount by which it fails to close, you can do a little calculation back of the envelope. You convince yourself pretty quickly that it's going to be proportional to the area of that loop. And so then, because the natural thing to do is you take a loop with a tiny area and you divide by the area, and then that gives you a quantity which is of order 1, and which only depends on the plane in which the loop lies, right, and the orientation of the loop. And so basically it just depends on two tangent vectors, right? And so that's something that now gives you a two-form, takes as an input two tangent vectors, spits out an element of the V algebra, which gives you the element in the tangent space, tells you by how much the thing fails to close up when you lift a little loop that lies in the plane spanned by the two tangent vectors, right? And that's the curvature tensor. So if you write things down in coordinates, you find some formula like this. So you can just take this as face value, but this is the geometric interpretation of that formula, right? So that's why it's the right formula. Okay. And now this is something which is intrinsic, right? So this does not depend on, right? So this is the geometric quantity. It doesn't depend on our arbitrary choice of origin for each of these copies of G in every point. And the whole philosophy in this business, right, is that relevant quantities, so the physically relevant quantities, should be the quantities that are geometric, so that don't depend on the parametrization. And so what does it mean? So it means that here there's a big group that acts on our fields, our space of fields, which is this group of sort of coordinate changes, right? And so if you do the calculation in coordinates, you find that these connections, these one forms, they transform like this. Okay, the exact formula doesn't matter, but like what you see here is that it transforms in the way you would guess, just by conjugation somehow, but then there's an extra term like that. And that's really because we're talking about a connection and not about one. It's exactly the same in Riemannian geometry. Remember, so this would be the analog of the Christoffel symbols, and the Christoffel symbols, if you remember your Riemannian geometry, they're like a quantity with 3 indices. And so every undergraduate gets confused because they think it's a thing with 3 indices, so it has to be a 3 tensor with, like whatever, 2 covariant, 1 contravariant or something index. But it's not, right? Because it doesn't actually transform like the tensor, because it actually represents a connection, not a tensor. And here it's exactly the same thing. So it's like if you look at the formula for the change of variables of Christoffel symbols, it has the same sort of form. It transforms like a tensor, which would be that bit, but then there's an extra bit. It's really exactly the same formula. And now, just because of that geometric interpretation, our action is invariant under, you know, this act. Okay, so the word action has two meanings here, right? So there's the action S, and it is invariant under the action of this gauge group onto our space of fields, right? So in the sense that S of AG, so here you find that S of AG is equal to S of A for every smooth function G. Right? So that's, now you can forget about geometry, right? Like if you don't like geometry, you can just do the calculation. Right? So it's something you can just check. Okay? That this expression here with this definition of F is invariant under this action. Okay? But now, what does it mean? So the problem is that, so remember, what's the thing that we wanted to do? We wanted to somehow define, right, these measures of the type e to the minus s of a, ba. This is like a Lebesgue measure. Now, what it means is that if you look at, you know, in the space of A's, so in our space of connections, now there's infinitely many directions in which the action is just constant, right? Because we just said that S of AG is equal to S of A for every G like that, and that's of course an infinite dimensional space. It is the space of all the smooth functions from the torus into that G. So you have this big infinite dimensional group that acts on this space of connections, and this action is just constant. That means that this quantity here is sort of flat in infinitely many directions. So it's not very coercive. And so obviously what this means is that, you know, since we already argued that there's no Lebesgue measure in infinite dimensions, it means that, you know, on its face, there's no chance that such an expression makes sense. However, we also just said that the relevant quantities are the ones that are gauge invariant. So that the ones that don't depend, the ones that are themselves, you want invariant under this action. And so what this means is that the real state space here should not be the space of A's viewed as one forms with values in the algebra, but it should be that space quotiented out by this action, right? Because all the quantities we care about are invariant under the action of this big group, and therefore different connections that are related by the action of that group should simply be identified. It should just quotient out the action of that big group. Now, of course, that, you know, is naively sort of solves that problem of non-coercivity of this action functional, right? Because now there's infinitely many flat directions, but we just say, well, okay, we view them as points. So that's our new space. And so, for example, so like here, I just mentioned Wilson loops. So Wilson loops, that's examples of quantities that are gauge invariant. And there are things exactly of, you know, like the way we define curvature, remember? You do that, but instead of taking infinitesimal loops, you take a finite loop. You take some loop of size about 1, you lift it, you look at what's the discrepancy, and then you take any class of. So now the discrepancy is not an element in the algebra in the Lie group, because it's going to be an order 1 somehow discrepancy. And then you apply some class function to that element, like the trace, for example, and that gives you a number, and that number, these numbers are gauge invariant. That's something again we want to check. And in fact, every gauge invariant observable is sort of that type. It can be approximated by a function. Observables of that type. So these are the relevant ones. And that's the analog of somehow local observables in this business. So now still one problem that you have is that when you do that quotient thing, So now your space becomes some kind of complicated nonlinear space. So like in general, that space of connections was linear, or at least it was affine, because there's no natural origin, right? So here there's an origin which is A equals 0, but B connection corresponding to A equals 0 is not something intrinsic because it depends on your choice of coordinates. It's not gauge invariant, so it's really an affine space, linear space, but still basically the same thing. But now that action is, you've seen the formula for it, it's clearly nonlinear in G. G is itself, well, that's not a linear object anyway. And so that quotient space is not a linear space. And in fact, it doesn't have, I mean, in general, it has sort of non-trivial topology. You cannot really have one nice kind of smooth global way of parameterizing like that locally, yes, but not globally. And also, even if you have some sort of local parameterization of that space, now it's much less clear what the measure should be, right? Because this, like the bag measure, okay, it doesn't exist on infinite dimensional spaces, but at least if the space is linear, we have some sort of good feeling of what would be a reasonable approximation of your bag measure. If that space is sort of nonlinear, anything could happen. Right? So it's much less clear what that measure would be if now your reference space is an infinite dimensional nonlinear space. So of course, like the construction of that measure. So now the thing that we want to build, right, like this measure, so it's called the Yang-Mills measure. And that's of course something that people have been looking at for a long time. So it sort of goes back to the 70s. So I'll give you a bunch of references here. The point here is that in 2 dimensions, miracles happen. And it's different miracles from the miracles that you feel familiar with, but still many miracles happen in 2 dimensions. So other types of miracles happen here. And the miracle is that, if you just like close your eyes and sort of pretend that the bag measure makes sense and so on, you can essentially guess a formula for the joint distribution of these Wilson loop observables. Right? So here, like the Wilson loop, remember, was you take an actual loop here, you lift it, you look at the discrepancy, you take the trace. So now that's a function of the loop and of your connection. Now, imagine your connection is drawn randomly according to that measure. Suppose you have some way of making sense of that measure. So now you have a probability measure on the space of connection. So you can draw a random connection, compute that Wilson loop that gives you a random variable, just a real valued random variable. If you have several loops, that gives you several real valued random variables. And so now what you can do is you can basically guess a formula for the joint distribution for these random variables for any number of loops. And so that in principle gives you a full characterization of this measure because I mentioned earlier that these Wilson loops are, if you want, like a full set of observables. Every function that is gauge invariant can be approximated by a function of finitely many Wilson loops. Okay? And so that completely characterizes this measure on the space of gauge orders, on this quotient space. So in 2 dimensions, you have this miracle, but you just have an explicit formula. So then the measure is sort of well defined in the sense that at least, K-loop distributions are well defined because you just have a formula for that. But then in higher dimensions, those miracles don't happen. And particularly, what one would be really interested in is constructing this in 4. Okay, so if you can do this construction in 4 dimensions, and furthermore prove additional properties, which would be extremely hard to prove, and do it on a sort of like the full space instead of the torus, then you could get the Yang-Mills variant on So it's probably not one of the easiest $1 million to get. But in 3 dimensions, there are sort of a bunch of results, and those are actually even in 4 dimensions. They suggest that somehow something is, so what they do is you look at some discretization, these measures, so there are natural discretizations, which are called lattice gauge theories. And then you show some type of stability as the size of the lattice goes to 0. But that type of stability goes nowhere near short any tightness thing or convergence of observables, or it doesn't even give a candidate state space for limiting measure or anything like that. Right? So it's a very weak from stability results. And there's in particular, there was a very long series of papers by Balaban in the 80s, and then the other papers built on that. But there's more recently, there's a paper, for example, by Karan Chatterjee, and actually Surab is here, not in this room, but is here today, and gave a talk yesterday. I think he's giving a talk this afternoon again. And with his PhD student Sky, they proposed the candidate state space a couple of years ago for the 3D sort of Yang-Mills measure. I'm going to mention a little bit more about that later. Okay, but so now, what are we going to do here, right? So remember, the aim somewhere would be to make sense of that measure. One knows how to somehow make sense of it in 2 dimensions, at least in some weak sense, like these K distributions have a meaning in 2 dimensions. In 3 dimensions, it's basically complicated. And then 4 dimensions would be the physical case, because the space here is really space-time. And then in dimension higher than 4, one doesn't expect this. So here the basic idea is to do what's called stochastic quantization, which was proposed by Parisi and Wu back in the early 80s. And that just relies on the fact that formally, if you have a measure like this, so imagine that phi is finite dimensional, so if phi just takes values of Rn, and you have a probability measure of that type for some smooth and sufficiently coercive functional S, then it's a fact that if you look at this stochastic differential equation, which is just a gradient flow, right? So this is sort of probabilist notation, think of dividing by dt on both sides. So then this is just gradient flow, so it tries to find the minimum of S, but then you add some noise. Okay, so the W here is a Brownian motion. So now the solution to this equation is not deterministic, it's random, because the Brownian motion is random. And it's a random process which has the property that if you draw the initial condition randomly with respect to this measure, then for any time, any fixed deterministic subsequent time, the solution is distributed according to the same measure. And if you start with any other, if you start, say, with a deterministic initial data, then the distribution is going to converge to this measure as time goes to infinity. Okay? So then one way of defining this measure is to define this process, and then the measure is just the invariant measure of that process, if it has one. And so that's the approach that we're following. So we try to, so what we want to do now is we want to look at the natural noisy gradient flow that's associated to this Yang-Mills function. So if you just do the calculation, you'll find something like this. dTA is equal to this here is just the sort of functional derivative of this guy. Okay, so that's your gradient S. And then your noise here. So remember, there's a thing here, is that when you have a gradient, implicitly it means that you've actually chosen a metric, right? Because the gradient is not an intrinsic bit. It's a differential, but then hit with the metric. And so here there's a covariance structure for this Brownian motion that you also have to choose, and the covariance structure has to be the one that's given by. Okay, so that's, if you want here, you have a choice of metric you can make. You can choose the corresponding covariance structure, and then what I said is true for every such choice. So here the natural choice is the L2 metric, which makes everything local. So if you take the L2 derivative of S, gives you this local quantity here. And so then a noise with the L2 covariance, sort of the corresponding covariance structure that corresponds to the L2 metric, is white noise both in space and in time. So because now our state space is this space of fields, or this space of one forms. And so the noise is not just the Brownian motion in time, so it's a Brownian motion in time with values in a space of fields. Right? And so you have to specify some covariance structure on your space of fields in order to define that noise. And in this case, it's the most uncorrelated covariance structure. If you want to, the psi is the thing that normally has a covariance structure with the expectation of psi is the next psi of y, it's just the delta and the time, delta next at y, and then because in reality, so this is all the algebra valued, right? And so your noise is also the algebra valued. And so then this is still something that takes values in the square, if you want, of the tensor square of the algebra, symmetric one. And then here it's times the Casimir operator, the algebra. Okay, so that's the natural noise here that drives this. But the point is that it's very irregular. So it's essentially, it's delta correlated in space, it's delta correlated in time. And this equation here you have an operator which is like a d star d, which looks like a Laplacian, but it's not, because here it's like a Laplacian on one forms. And you know that, well, it's half of a Laplacian on one forms. Right? The Laplacian on one forms would be d star d plus d star. And if you take only one of the two halves, then maybe you remember that that's actually not an elliptic operator. So this equation is not quite parabolic, because this guy is very degenerate. And that's just the reflection of this big symmetry. So we cannot expect to get something parabolic, because that would mean that it's sort of corrosive in all directions. It's not. However, here there's a trick we can play. That trick was first invented by the Turk in the context of Ricci flow. But then Donaldson realized in the early 80s that you can apply the same trick for the Yang-Mills flow. And the trick here is to say, well, remember, at the end of the day, we're going to quotient out by the action of this gauge flow anyway. And so it means that if now, imagine I draw a picture of the space of A's, and so now the board is the space of connections A, and you have this group action that acts on it. So you have orbits, like for every A, there's a bunch of AGs. So of course, all these things are infinite dimensional. It's infinite dimensional orbits, and now we want to define some kind of stochastic differential equation, which gives you some stochastic process on that space. But then at the end of the day, we're going to consider each orbit as a point. And so we can actually modify the equation. So if we add an extra drift that just moves along the orbits, that doesn't do anything by the time you quotient out. Right? So it gives you a different equation, but by the time you identify all the points in an orbit, it doesn't make any difference. Right? So you can add anything which points along the direction of the orbits. And so it turns out in this business that you can actually add anything of the form dA, so dA is some kind of exterior derivative, it's like a deformed exterior derivative of any functional that you want, right? So these are the vector field if you want the point in the direction of the gauge orbits. And so then here I can make the choice A of H of A for D star A. And so then you have the missing DD star term to turn it into a Laplacian. So that's what's the trick that was somehow realized by de Turck and Donaldson in the 80s. And well, okay, so that was just a picture which explains the same thing. And so when you do that, you end up with an equation which is at least parabolic. So you end up with an equation for A, which is like a heat equation. It has this white noise, and then it has some bilinear term in A on its first order derivatives and some trilinear term in A. Okay, and I don't go into the details of what this bilinear term exactly is and what the trilinear term exactly is. But now here you have another problem, right, which is the problem that you often have in quantum field theory, which is that you end up with nonlinear operations that are not well defined because the objects are not sufficiently regular. So like if you forget about these nonlinear bits here, and you take just the heat equation plus noise, the solutions to this equation for any fixed time look like what's called the free field. And the free field has regularity almost zero, but not quite. So in 2 dimensions, it's a distribution, but it's like barely a distribution. It's very much almost a function. In 3 dimensions, it's really a distribution. It has regularity minus a half, and you sort of lose half of the derivative as you go up for every dimension. Right? So in dimension 4, you will have regularity minus 1, in dimension 5, minus 3 half, and so on. So you cannot expect the solution here to have regularity better than minus a half. And so then here you have to, well, basically multiply 3 guys that are 3 distributions of regularity minus a half, and you have to multiply the distribution of regularity minus a half with another one of regularity minus 3 halves, the derivative. Of course, you can't do that. There's no canonical meaning for these products. But then, so here, that's what this theory of regularity structure does for you. It basically says if you have an equation of that type under some power counting condition, which is satisfied in this case, you can smoothen out the noise in pretty much any way you want. Then, of course, you have solutions, right? So smoothing out basically means replacing that delta function by some epsilon approximation to a delta, right? Something like that. And now everything is smooth for fixed epsilon, so all the operations are perfectly well defined. And then you want to set epsilon to 0. And what the general theory tells you is that, well, in general, the solutions don't converge. Epsilon goes to 0. But you can add some finitely many counter terms to the equation that make it. Okay, and then there's a formula for these terms. And if you check on that in this particular case, it tells you that you just have to add a linear term of this. Okay, with C just a constant, a real constant. Okay? At least in the irreducible case. So in general, like if your Lie group is like a tensor product of 2 different groups or something, then maybe you have a different constant of the different blocks. But basically, this is just a constant. Okay? So then so the general theory tells you now you regularize it in pretty much any way you want. You can find a constant depending on epsilon, which blows out if epsilon goes to 0, so that this family, the family of solutions to this equation have the limit of epsilon goes to 0. And if you choose the constant in the right way, you can even do it in such a way that the limit doesn't depend on your choice of approximate delta function. Okay, so that's really good. That's all the thing we want. Except that there's 2 things that are bad here. The first one is, remember the whole thing was about at the end of the day, you want to quotient out the action of this gauge over. So what it means is that we would like our process to have the following property, is that if you take two starting points on the same orbit, right, you take that solution and you take that solution, and then you quotient out, right, the two solutions, you project them onto the quotient space, you should get the same, at least in law, right? Like the solution should not depend on where you start on the gauge orbit. So you want to really build a process on the quotient space and not on the full space. Right? The one on the full space we don't care about. We only care about the one on the quotient space. And if we want that to be sort of canonical, then it better be that you don't depend where you start on each of these orbits if you want to identify these points. Right? And that, at least formally, one can kind of check that this equation has that property. But this one does not. Basically, because of the fact that you've replaced that delta function, it sort of the calculation uses the fact that the covariance of the noise is exactly delta function. If you replace it by an approximate delta function, it kind of breaks that one. And the other problem that you have is that, well, I wanted to kind of look at this equation, but now the theory tells me I have to look at this equation, which looks different. And then again, that's just not the equation I wanted. And this term by itself also looks like it breaks this gauge invariance in the sense that this gauge invariance property, so the property that the law of the solution projected on the quotient space doesn't depend on where you start on the orbit. It's a very rigid property, right? Like if you ask yourself which equations have that property, there's pretty much one equation you can write down. If you don't want the derivatives of high order shown now, then this equation is, like these terms here are completely specified by that property. Right? So you cannot just add a term like that and expect that property to still hold, right? And the other thing is that now here we don't get one limit, right? So I mentioned if you choose that constant in the right way, you get a limit, and the limit is independent of. Okay, that's fine. But you still have a one parameter family of limits because, if you have one choice of the constant C epsilon that gives you a limit, which independent of the choice of regularization, but now I can take that particular choice plus one, that's also going to give me a limit. It's going to give me a different limit, right? Which is a different limit that does not depend on the choice of regularization, but you have, there's a one parameter family of natural limits that show up here, which is sort of given by the finite parts of that kind of infinite constant. Okay? And well, then we wanted one guy, so now we have a whole one parameter family. Okay, so which one's the right one? And so then the hope is that, well, since in a way this guy breaks gauge invariance, but the regularization that we did on the noise also breaks the gauge invariance. If you're really lucky, maybe the two cancel out. And in the limit, you actually recover this gauge invariance. Okay, and so that's basically what the theorem says. So there's in 2 dimensions, so we have a result in 2 dimensions and in 3 dimensions. And from the point of view that I just explained, they both say the same. But there is exactly in that one parameter family of limits, there is exactly one guy which has that gauge invariance problem. Therefore, that's the correct one. And furthermore, in 2 dimensions, we have a bit more, which is that we have a really nice state space, right? Because now there's a question of how to actually, doing that quotienting procedure, okay, this is like on the hand-wavy level, perfectly fine. But now at the technical level, if you think about it, it becomes really tricky because the space of A's, so first the space of A's really has to be a space of distributions, right? Because the solution is going to be like a distribution of regularity minus a half or minus epsilon in dimensions. But then already, the A's are supposed to be one-forms. So the whole point is you want these Wilson loop observables, right? Where you sort of take a horizontal lift, use the A to lift quantities according to a loop, and then looking at what the discrepancy that you get. Now, if the A is the distribution, in general, you cannot even restrict the distribution to a curve, right? So it's kind of tricky to even find a space of distributions that is big enough to contain solutions to this equation and small enough so that you can actually restrict them to any smooth curves and that you can perform these horizontal lifts. And so in 2 dimensions, part of the statement, if you want, some of the main technical statement actually is the fact that you can do that quotient procedure in a nice way. So you can find a nice space of distributional connections for which you do have a notion of horizontal layer, but which is large enough so it contains the solution to this equation, and which is such that your gauge group acts on it in a nice way, because then, what functions if you take smooth functions, it's sort of clear what the action is, but the problem is that your orbits are not going to be closed sets, and so your quotient procedure is not going to be nice, right? But then if you take less smooth functions, the quotient procedure becomes nicer, but at some point you run into the trouble that even the change of variables formula, like the formula for AG, stops making sense if G is too rough, right? So here, the claim is that you can build the space in such a way here that if you take precisely the Hilbert continuous guys for some specific exponent, the quotient space is actually a nice Polish space. So the quotient, it's compatible, if you want, with that quotient procedure. And so in the end of the day, you really get a Markov process on a nice state space. So you can perform that quotient procedure, you get a Markov process on a nice state space. And in fact, there's a very recent result by Ilya and Hao, which says that that process that we construct really has an invariant measure. It has a unique invariant measure, and it's on a state space for which these Wilson loop observables make sense. And you can look at the joint distribution of these Wilson loop observables under the invariant measure, and it is exactly the one that was guessed by the physicists in the 70s. So that kind of closes, if you want, the whole thing in a rather neat way in 2 dimensions. And in 3 dimensions, you end up with various problems, which is that, so for example, in 3 dimensions, we were not able, so first, these Wilson loop observables cannot really make sense in 3 dimensions, because if you take the 3-dimensional, even the free field, you cannot restrict it to a curve. As the 2-dimensional free field, you can restrict it to a curve. Okay? So there, the Wilson loop observables don't make sense. So you can still, what we can do is we can find a state space on which some kind of smoothed out version of the Wilson loop observables makes sense. Where the smooth name, you have to do a smooth name, which is itself gauge invariant. So you cannot just convolve with a modifier. That's not the gauge invariant procedure. Pretty much the only thing you can do is you take the deterministic Yang-Mills feature, like the gradient part of our gradient field, without the mods, just the gradient descent part. That's a nice parabolic PD. So that gives you a smooth procedure, which is gauge invariant. We'll call that. And so then you can use that. Now, the thing is that you end up with the problem is that actually your solutions are sufficiently rough so that you're even out of the domain of well-posedness for the deterministic parabolic PD. So like you cannot even find, you can have a theorem that somehow says it's impossible to find any Banach space which on the one hand is large enough so that it contains samples of the free field, and on the other hand is small enough so that the solution to the parabolic guy is continuous. Right? So already at the level of the deterministic part of the equation, like not even talking about the noise, which causes all the problems with optimization and so on. So even just the deterministic bit, it is not possible to find any Banach space for which that part is well posed and which is large enough to contain candidate solutions for our equation. Right? So already there you have to find a nonlinear space. Okay, but you can do that, and that's very similar. That part is very similar to what Surav did in the PhD scheme. Okay. But then you end up with, well, okay, so somehow there's a similar type of result in 3 dimensions, which, as far as identifying the process is concerned, is the same as in 2 dimensions, in the sense that there is, you have this one parameter family, and there's exactly one guy that has gauge invariance property. And then you can build a state space that goes with it. It doesn't have quite as nice properties as 2 dimensions. For example, we couldn't make it a whole space, whatever, but at least it's sort of just about nice enough that probability theory works okay. And it's also just about nice enough so that you have these smooth networks and loop of 0. So, right, and so that, so that was that remark, is that the state space that we use is very similar to the one that Hao and Chatterjee proposed. That proposal was sort of done independently about the same time, but it's a very natural construction if you want. It's a little bit smaller because we have, so it's like in the construction of dynamic, somehow there's various constraints that you need to satisfy, which that space did. So you need to make it a bit stronger, but it's a very similar kind of space. Okay, so maybe I should stop here. So maybe I just mentioned, like, okay, the main open problem in this business, this stage, is in 3 dimensions, right? So we have built that process, and now, okay, if you want that measure, you would want to define it as being the invariant measure of that process. Now we know that if that process has an invariant measure, then it is unique. Okay, so that will give you some sort of uniqueness of that measure. So the construction of the measure, the only thing that we don't know is that it actually has an invariant measure. And so, like the process that we build, we get short time control of it, but it may, as far as we know, it may blow up in finite times in the space of gauge orbits. Obviously, nobody believes it, but it's very difficult to get global solutions. I mean, just to, if you remember the equation in terms of scale, remember there was a cubic term and there was a quadratic term, which was like bilinear in A and its first order derivative. That's exactly like Navier-Stokes, and with 3 dimensions, right? So it scales exactly like Navier-Stokes. It's a bit better because your energy, this Yang-Mills energy here, looks more like an H1 mode. Okay, and if you had H1, preservation of H1 from Navier-Stokes, then you wouldn't be in business. So for example, so for the deterministic part of the Yang-Mills heat flow, it's known that the classical result from the 90s or something, that you do have global solutions. You have unique global solutions. But here, of course, solutions are so irregular, you're really extremely far from being H1, so you have no idea what to do. Good point to start. Thank you very much.